Good day, my name is Abella and this is Engineering 211 Mechanics of Deformable Bodies. In this presentation, I will be discussing thermal and mechanical axial displacements, principle of superpositions, and determinate versus indeterminate structures. Our objective for this presentation is to understand the key concepts and their applications in structural engineering and problem solving. First topic is thermal and mechanical axial displacements. First is the thermal axial displacements, refers to the change in length of a material due to change in temperature. And we have the given formula, L is equal to alpha, sum of L, and T, where L is the axial displacement, and the symbol alpha is the coefficient of linear expansion, and L is the original length, and T is the temperature change. Second one is the mechanical axial displacements. It is the change in length due to axial forces. It will be whether be tension or compression. Our formula is L is equal to FL over AE, where L is equal to axial displacements, and L sub of 0 is the original length. A is equal to cross-sectional area, and E is the Young modulus. We have the sample problem 1 regarding thermal axial displacements. Steel rod of length 3 meter and a cross-sectional area of 0.01 meter squared is heated from 20 degrees Celsius to 60 degrees Celsius. The coefficient of linear expansion for steel is 12 by 10 raised to negative 6 degrees Celsius, negative 1. Calculate the actual displacements of the rod. We will be determining the given initial length. L sub of 0 is equal to 3 meter. Temperature change. Increment of temperature is equal to 60 degrees Celsius minus 20 degrees Celsius is equal to 40 degrees Celsius. And the coefficient of linear expansion for steel is the alpha is equal to 0.00012 per degree Celsius. The formula is change of length is equal to alpha, length sub of 0, change of temperature. Substitute known values, we will arrive. The actual displacements of the rod will be 0.00144 meter. Sample problem number 2. Mechanical axial displacements. A copper rod of length 4 meter and a cross-sectional area 0.005 meter squared is subjected to a tensile force of 500 Newton. The Young modulus of copper is 1.1 times 10 raised to 11 Newton per meter squared. Now let's calculate the mechanical axial load. We have the given length is equal to 4 meter. Cross-sectional area is equal to 0.005 meter squared. The force is equal to 500 Newton, and the Young modulus is 1.1 times 10 raised to 11 Newton per meter squared. We have the formula. Change of length is equal to force times length of 0 and all over the area and the Young modulus. And computations will give us the mechanical axial load of 0.00003636 meter. The second topic is regarding principle of superposition. What is a principle of superposition? Principle of superposition states that in a linear system, the net response or the displacement, force, etc. caused by the multiple load is the sum of the individual responses caused by each load applied separately. We have the formula. Delta total or net is equal to delta 1 plus delta 2 plus delta n, where the delta net is the total displacement due to all loads, and the delta sub of I are the displacement caused by each individual load. Our key assumptions here is the system behaves linearly and the principle holds for the elastic materials where the relationship between force and displacements is linear. We have a sample problem. A beam subjected to 2-point loads at different positions produces a deflection described as delta 1 is equal to alpha 1 P1, where P1 is 10 kilonewton and the alpha 1 is 0.002 meter per kilonewton. And the delta 2 is equal to alpha 2 and P2, where P2 is equal to 8 kilonewton and the alpha 2 is equal to 0.0015 meter per kilonewton. And we will find the total deflection at the midpoint of the beam due to the superposition of the two loads. The solutions, the principle of superposition states that the total deflections delta net, sum of net, is the sum of the deflection caused by each load. Formula, we have the delta net, sum of net, or is equal to the Q L delta 1 or plus delta 2, where delta 1 is equal to, upon computation, will give us 0.02 meter, and delta 2 will give us 0.012 meter. Substitute the known values, you will arrive at the delta net, or the sum states of the total deflections. Principle of superpositions will give us delta net is equal to 0.032 meter. Sample problem 2. A rectangular beam is subjected to two separate bending moments at different points along its length. We have the moment M1 is equal to 10 kilonewton meter, causing a maximum bending stress of alpha 1. Let's put the symbol again, and the beam given by symbol is equal to M sub of 1 C all over I. Moment M2 is equal to 6 kilonewton meter, causing a maximum bending stress in the beam given by the symbol is equal to M2C over 1, where C is equal to 0.05 meter. This is the distance from the neutral axis to the outmost fiber. And the I is equal to 0.004 meter raised to 4th power, moment of inertia of the beam cross sections. We will determine the total bending stress of the outermost fiber of the beam due to the combined effect of the moment. Solutions. Calculate for alpha 1 caused by M1. We will arrive as 1250 kilonewton per meter squared. And calculating the alpha 2 caused by M2 will give us 750 kilonewton meter per meter squared. Now apply the principle of superpositions. The total bending stress is the sum of the individual stresses. And now we have the total is equal to alpha 1 and alpha 2 is equal to 2000 kilonewton per meter squared. And the last topic is the determinate versus indeterminate structures. Now, for determinate structures, it states that structures where the internal forces and reactions can be determined using equilibrium equations alone. Example, the number of unknowns is equal to the number of equations. The common uses, simple to analyze, quick design and cost-effective, ideal for temporary or simple loads. For the applications, short span bridges, trusses for roof systems and small building, scaffolding and temporary support systems, cranes and lifting arms, and railway track supports and simple platforms. For indeterminate structures, structures where additional equations such as compatibility and material properties are needed to determine the internal forces and reactions. Example, the number of unknown exceeds the number of equilibrium equations. The common uses is more stable and rigid, better at distributing loads, can handle complex variable or heavy loads, and safer under support settlement or idle loading. Applications to continuous bridges with multiple spans, high-rise building and towers, reinforced concrete frames in commercial building, and aircraft and vehicle cranes. Now, for example, problem regarding determinate structures. A simply supported beam spans 6 meters with a point load of 10 kilonewton applied at 3 meters from the slab support. Determine the reactions at the supports. Solutions. Calculate the support reaction using the equilibrium equations. Sum of the vertical forces is equal to summation of forces from the vertical is equal to 0. Ra plus Rb minus 10 is equal to 0. Sum of moments about point A, summations. Ma is equal to 0. It's minus 10 times 3 plus Rb times 6 is equal to 0. Solving these equations from the moments, it will give us R to the sum of B will give us 5 kilonewton. And from the vertical forces, Ra is equal to 5 kilonewton. Now the reactions. This structure is statically determined because all reactions are solvable using equilibrium equations. Next, sample number 2, indeterminate structures. A beam is fixed at both ends and spans at 8 meters. A uniform distributed load, or UDL, of 2 kilonewton per meter is applied across the entire span. Determine the reaction at the supports. Solutions. We will formulate the equilibrium of equations. Sum of the vertical forces, that would be Ra plus Rb minus 2 times 8 is equal to 0. Sum of moments. With the fixed end moments, it needs to be considered. Use of additional compatibility equations. So the fixed end moments and the deflection conditions for indeterminate structure requires calculation involving material properties. Examples, E and I, the Young modulus, and beam deflection formulas. The reactions, this structure is statically indeterminate because additional compatibility equations are required beyond the equilibrium. So that will be the simple presentations for the course Engineering 211, Mechanics of Deformable Bodies. Again, we have the topics discussed are thermal and mechanical axial displacements, principle of superpositions, determinate versus indeterminate structures. And thank you. This is Abella again, and have a good day.